Yeah, as said, I'm going to talk about conjugacy classes of integral matrices, so matrices with integer coefficients, and fractional ideals of orders, and what is the relation between the two things, and how we can compute everything that I just said. Yeah, so I cannot see the chat at the moment, so if there is any question, please, I ask the organizer to interrupt me any moment. And also, if there is any problem with the slides or my volume, please give me some kind of sign. So I will keep like your faces on the side. All right, let's start. So the plan for today is the following. So first, we're going to talk about conjugation, so matrices, square matrices, and how we can relate the two of them by multiplying by invertible matrices and yeah, conjugation. Second, I'm going to talk about fractional ideals. And how do they behave with respect to isomorphism? Yes, class groups are going to appear in this talk as well. I know that there are big fans of class groups in the audience, but we are not going to just consider invertible ideals of maximal orders, but also ideals of non-maximal orders, and in particular, non-invertible ideals. There is a connection between matrices and ideal, as I mentioned, and this is given by this old theorem by Latimer and McDuffie. I think it goes back to 1933, so it's pretty old. As I said, this is going to be a computational talk, so I'm going to explain algorithms to compute the ideal classes and how can we determine from the ideal classes if two matrices are conjugate. And then in the last slide, I'm going to give like a bunch of generalization of the algorithms that I will present in this talk, and also some other application of these ideal classes computations. All right, let's start from the beginning. So the conjugacy problem, it's pretty natural. So you start with a ring. We want this ring to be commutative and have one inside. We take two matrices, A and B. These are asked to be square matrices, n times n, with coefficient in our ring times CR. And we say the two matrices are conjugate of this ring if there exists an invertible matrix with coefficients in R as well, such that A is equal to U times B times U inverse. All right. So if you think of A and B as operators acting on some free R module, then U is going to correspond to a change of basis. It's going to tell you what happens if you change the base of the operator B and if you get actually the matrix representing the operator A. Cool. So a natural question is that, okay, if I just give you these two matrices, A and B, so you have like a bunch of R elements inside, these are the coefficients, can you determine just by looking at them if they are conjugate? So this is a very vague question, and there is a reason why it's vague. I'm going to make it very precise later. And the second question is that, are the invariants that determine the conjugacy class of a matrix, and are they easy to compute? And second of all, if we fix this invariant, can we also represent all the conjugacy classes with that fixed invariant? Okay. So let's talk about these invariants. So the first one that one can think of is the characteristic polynomial. So when you take a square matrix, you can compute the characteristic polynomial of this matrix, which is defined as the determinant of variable times the identity matrix minus A. This is going to be a polynomial of degree n, so the same as the size of the matrix, with coefficients in R. It's easy to prove by the properties of the determinant that the characteristic polynomial is an invariant of the conjugacy class of A. But it's very easy to find examples that show that this is not a complete invariant. Namely, if we take the following two 2x2 matrices, A, which is the upper triangular matrix with only ones, and B, the identity matrix, they have the same characteristic polynomial, x minus 1 squared, but they have different minimal polynomials. So the first matrix has a polynomial of degree 2, x minus 1 squared, while the second one, clearly the minimal polynomial is x minus 1. So recall that the minimal polynomial of a matrix is the polynomial of smallest degree, which has A as a 0. So when you apply A, when you put A instead of the variable, you get the 0 matrix. Okay. And one can prove that these two matrices are not conjugate over any ring R. So there is really no constraint. It can be a field, can be a PID, can be a finite ring. Okay. Now, let's for a moment focus on the simplest case. So when our coefficient ring is actually a field. This is done in the first year of mathematics. So I mean, this is just linear algebra. I'm just going to review like what's the situation, because we're going to try to generalize and go further. So over a field, the minimal polynomial and the characteristic polynomial of a matrix tells us almost everything we need to know about the conjugacy class. So more precisely, there is this thing called rational normal form, or sometimes also called Frobenius normal form of a matrix, that tells us that there is a sequence of polynomials, G1, G2, GR, each one dividing the next one in the sequence, and the first one is the minimal polynomial of the matrix, and the last one is the characteristic polynomial of the matrix, that completely determine the conjugacy class of our matrix, A. All right, so if we know this polynomial, if we know these polynomials, we know everything we need to know about the conjugacy class of the matrix. In particular, one can also prove that our matrix is going to be conjugate over R to the companion, to the direct sum of the companion matrices of this polynomial. I'm not going to get into detail, for there is no need to for the purpose of this talk. I just want to say that this is also computationally very nice, because this polynomial can be easily computed from the Smith normal form of the matrix, and there are very good algorithms to compute the Smith normal form. All right, and in particular, if the characteristic polynomial is irreducible, so if we add this additional hypothesis, the problem is completely solved. So we know everything about the conjugacy class of the matrix. So there is nothing else, and no other determinants are required, and the characteristic polynomial is going to be a complete invariant of the conjugacy class. Great. But now we're going to change our setting. So R is not going to be a field anymore, but it's going to be a ring, and we are going to work over the simplest ring that we can think of, namely the ring of integers, Z. And we are going to require that the characteristic polynomial is irreducible. So I'm going to denote the characteristic polynomial by H. So this is going to be a monic irreducible polynomial with integer coefficients. And now, given two matrices, n times n, where n is the degree of the polynomial with integer coefficients, and we require also that they have the same characteristic polynomial, can we determine if A and B are conjugate? And second question, can we list representatives of the conjugacy classes of matrices with that characteristic polynomial? And also, is this a finite set? So we have just seen in the previous slide that over a field, there is only, this set consists only of one element. And I'm claiming here, since I'm posing this question, that this is not the case in general over the integer. So the situation is a lot more complicated and cannot be solved just by you doing linear algebra. Or better, I mean, you can say that we're doing linear algebra over the integers, which is another name for number theory. Okay, these are the questions that we're going to focus on. So determine if two given matrices with the same characteristic polynomial are conjugate, and second, list a representative for the conjugacy classes. So we want a bunch of matrices as output of our algorithm. So yeah, I already said, yes, we can answer positively these two questions. So we're going to have an algorithm, in the end of this talk, we're going to have an algorithm that tells us if the matrices are conjugate, and we're going to have an algorithm that spits out these representatives of the conjugacy classes. So, right. But first, before getting there, I'm going to need to introduce some notation and some background material that maybe you're familiar with, but nevertheless, let's go. So as before, H is going to be a monic irreducible polynomial with integer coefficients. I'm going to denote by K the number field defined by this polynomial H. Okay, so just polynomials over Q modulo the idea generated by this polynomial H. I'm going to denote by alpha throughout this talk the class of X modulo this polynomial. So this is going to be a root of the polynomial, but I don't want to think of this root as embedded inside, let's say, the complex numbers. So it's going to be just algebraically, okay? An algebraic element. Okay. So an order in this number field K, an order R, is a subring of the field, it's a subring of K, which is also whose additive abelian group is free of maximal rank. So it's isomorphic as an abelian group to Z to the power a degree of the polynomial. Okay. So examples of orders are the monogenic order or equation order, if you're a magma user. So Z alpha, which is just Z plus Z times alpha plus Z times alpha squared, and so on up to Z to the power, Z times alpha to the power n minus 1, where n is the degree. Another example is the maximal order of the number field, also known as the ring of integers of the field. Sometimes these two concepts coincide, sometimes they don't, depends on many things. For example, it depends on which polynomial do we choose to represent our number field. And another concept that I will use is the concept of overorder. So if we take our order R, an overorder is any order containing R, or in other words, it's a ring that contains R and it's contained in the maximal order. So necessarily, an overorder is also a free abelian group of maximal rank. So it's an order itself. Okay. All right. Great. Another thing that we are going to use a lot is the notion of fractional ideal. So a fractional ideal of any order R is a sub-R module of the number field. And we require the submodule also to be a free abelian group of maximal rank. Examples of fractional ideals are every ideal which is non-zero. Every ideal of the ring which is non-zero is going to be a fractional ideal. Necessarily, it will have maximal rank. But we can also take modules of the form 1 over something times R. This is also going to be a fractional ideal. And by the definition that I just gave before, also any overorder of R is a fractional ideal. So any overorder is going to be closed by multiplication by elements of R. So in particular, it's an R module. It lies inside K, and it has the right rank as a free abelian group. So overorders are also examples of fractional ideals. All right. Given two fractional ideal, we can operate on them by the usual operations. So we can multiply them, we can take the sum of the two ideals, we can take the intersections, and these are all going to be fractional ideals. And we can also construct the colon ideal. The colon ideal, or inverse ideal sometimes called, is the set of elements of the field that sends the ideal J inside I. So this is the colon I over J, or I colon J. And this is also a fractional ideal. It's not hard to prove that. Maybe I should mention also that all these operations can be performed in polynomial time. So given Z bases of the ideal I and J, we can compute all the others in polynomial time. And it's not hard to prove, and everything boils down to compute some hermit normal form of the matrix representing the basis. So everything is all very easy from the computational point of view up to now. Cool. So we say that two fractional ideals I and J are isomorphic if there exists an element of the field that sends one into the other. So such that Z times I is equal to J. All right. And the notation that I use is this isomorphism with an R. And this is just to say that it's the same thing as requiring these fractional ideals to be isomorphic as R modules. So you can prove that every R linear homomorphism between fractional ideals is going to be multiplication by a non-zero element of K. And if we want this to be an isomorphism, this must send one into the other. So we require equality. So the notation is not randomly chosen. Another equivalent way to say that two ideals are isomorphic is to ask that one is equal to the other times a principal ideal. So in particular, this will be the principal ideal generated by Z. So these are all three ways to define exactly the same concept. In this slide, I will use the notation square bracket to denote the isomorphism class of an ideal I. Okay, and now I define. So, okay, I'm sure that you understand already that this isomorphism notion induces an equivalence relation on the set of fractional ideals. And whenever you have an equivalence relation, we always try to take the concept, to take the quotient. And I'm going to call the set of isomorphism classes of fractional ideal, the ideal class monoid of the order R. Okay. Note that the monoid struction is induced by ideal multiplication. So ideal multiplication is compatible with the notion of isomorphism. If you take two ideals that are isomorphic and take other two, you multiply them, the products are going to be isomorphic as well. So we get an induced monoid structure on the set of fractional ideals. All right. I guess this definition reminds you of the concept of the class group of a number field. So this is a particular case, it's a special case of ideal class monoid. Namely, when the order R is the maximal order, the ring of the integer, the ideal class monoid is going to be exactly the class group. But I'm going to go back to this later. This is just to tell you that this is something familiar, not something super exotic. All right, so but let's get immediately to the theorem, the main theorem that gives us the connection between the conjugacy classes of matrices and this object that I just defined. So this Latimer-McDuffie theorem from 1933. So let H a polynomial as before, so monic irreducible with integer coefficients. There exists a bijection between the monoid of the ideal classes of the monogenic order of the field, so the order Z alpha, and the conjugacy classes of integral matrices with characteristic polynomial equal to the polynomial H. So this tilde Z means conjugation, as I defined it before. Okay, so I'm going to tell you what this bijection is, and actually I'm going to sketch the proof of this theorem. Just maybe, is there any question about the statement of the theorem? Maybe this is a good moment.
There's nothing on the text.
Okay, cool, thank you. So let's try to give a sketch of the proof. So we start with a fractional ideal, and I'm going to express it as with a z basis. So the z basis is going to be x1 up to xn, and it's going to be the degree of the polynomial now. And to this, so this is a z alpha module. So it's particularly, it's closed under multiplication by the element alpha. So when I represent the matrix that multiplication by alpha with respect to this z basis, I will get a matrix with integer coefficients, which I will denote with this m alpha ix. So this depends on the ideal, or actually more precisely depends on the z basis, is x1 to xn. And by construction, it's easy to verify that this matrix has the right characteristic polynomial. So it's characteristic polynomial precisely h. Note that if we change the z basis of this module, of this fractional ideal, we are changing the matrix, we are replacing the matrix with a z conjugate one. So this is just a z base change. So we are acting by conjugation with an invertible matrix with integer coefficients. And second thing, if you replace the ideal I by an isomorphic ideal, and consequently we replace this chosen z basis by the same basis multiplied by z, the matrix doesn't change, clearly. The multiplication by alpha will stay the same. So this proves that we have a well-defined map from the the monoid of ideal classes to the set of conjugacy classes of matrices. Okay, so this is one direction of the bijection. And in the other direction, so we pick our matrix A with the right characteristic polynomial, with our irreducible characteristic polynomial H. Oh yeah, I think I should have put this n equal to the degree already above, but now it's on the slide. We can induce a Z alpha module structure on the free abelian group of rank n in this way. So we define the multiplication by alpha on any integer vector as A applied to this vector, so this matrix A applied to the vector. Second, we pick any isomorphism of Q vector spaces. So K is going to be a Q vector space of dimension equal to the degree of the defining polynomial. And so we pick any isomorphism between K and Q to the power n. And we define I to be the pre-image of this free abelian group via this chosen isomorphism. And observe that so I, this ideal I, is actually, sorry, this set I is actually a Z alpha module, is an ideal, and the matrix A is going to represent the multiplication by alpha on I with respect to the basis X, which is the pre-image of this isomorphism of the standard basis of the free module. All right. So to every matrix A, we have associated an ideal, and it's an exercise to prove that this is well defined. And actually, this construction is the inverse of the construction that I described in the first half of the slide. And in particular, this is both inverse, and we get the bijection in the statement. All right. So I think the important thing that I want you to keep in mind from this proof is that it's constructive. So if I give you an ideal, there is an easy way, a computational way to construct a matrix, and vice versa. From the matrix, we can explicitly construct this ideal. So this is very, very easy to implement. So this is the key point. that I would like to remember. Great. Yes, so let's give an example. So we take a polynomial of degree 3. So this is going to be x to the power 3 plus 10x squared minus 8. Let Q alpha be our number field. So, okay, I'm claiming that this polynomial is irreducible, and Q alpha is going to be the number field that we look at. We consider the monogenic order with its power basis. I claim that Z alpha has two proper overorders. So two rings that are bigger than Z alpha, and there are also orders. So O is going to be the maximal order. This is the Z basis of the maximal order in this case. And then there is also this S, this ring. This is a Z basis of the ring. Using the algorithm that I will present in the second part of the talk, we get that the ideal class monoid of the monogenic order consists of 4 classes. So there is the alpha, there is this overorder S, there is the maximal order, and then there is this fourth mysterious element, ST. I will tell you everything about this ST later, but so far you have to just be happy with the Z basis. So this is a Z basis of this ST. And I'm claiming that this ST is not isomorphic to any of the previous 3 isomorphism classes, and also I'm claiming that there is nothing else. So we have 4 isomorphism classes for this order Z alpha. And what about the matrices? Well, you follow the proof that I described before, a couple of slides ago, a couple of slides before, and you get these 4 matrices. So the isomorphism class corresponding to the monogenic order will correspond to this matrix. This is actually the companion matrix of the polynomial defining the field. This weird mysterious ST is going to correspond to this matrix, S is going to correspond to this one, and the maximal order to this one. All right, 4 matrices, and by the theorem, these are all non-conjugate with each other. They are all different, and they correspond to all the representatives of conjugacy classes of matrices with H as characteristic polynomial. Right, so this is to prove that the algorithm actually works. Great. So are there any questions? So, all right. So in the rest of the talk, I will describe the algorithm to compute this ideal class monoid for any order in a number field K. So I'm not going to focus on the case of monogenic order, so any order. And second, I'm going to give you an algorithm to test whether 2 ideals are isomorphic, which in return will tell you like when 2 matrices with the right characteristic polynomial are conjugate over the integers. Great. So as before, again, R is any order in a number field K. Recall that a fractional ideal I is called invertible if I times R colon I is equal to the order itself R. So there are a bunch of different equivalent definitions of invertibility. So another one is that I is invertible if there exists another ideal J such that I times J is principal, or another one is I times J is equal to R, but they are all equivalent. So, and this one I think is the most direct one. So you take I, you compute the colon ideal R over I, and you check if the product of the 2 is the ideal generated by 1 or the order itself. Good. So we can define the picker group of the order R as the set of invertible fractional ideals modulo the isomorphism relation that I've defined before. So this is actually a group because we are looking at invertible ideals, and not so surprisingly, the inverse ideal, the R colon I ideal, is going to be the inverse, the class of this ideal is going to be the inverse of the class of the ideal I. So we have a group structure here. While on the ideal class monoid, when we look at all fractional ideals, we don't necessarily have inverses. So that one is just a monoid. So this picker group can be efficiently computed if we know the class group of the field, here's the class group, and the unit group of the number field of the maximal order. The way to do it is to look at this exact sequence, this 5-element exact sequence, where the first element is the unit group of the order R, the second one is the unit group of the maximal order. Then we have this ray class groups, or I don't know how they're called, this O modulo the conductor of the order R, and then you take units, and then the same as R over S. Then next there is the picker group of R that we are interested in, and in the end there is the class group of K. So we have always a surjection of the picker group onto the class group, And Kluners and Pauli in 2005 explained how to efficiently compute the term in the middle. And in return, this gives us an efficient algorithm to compute the picker group of any order, and also to an efficient algorithm to solve the discrete logarithm problem. So if you pick an invertible fractional ideal, we can efficiently compute what is its class inside an abstract representation of the picker group of R. So, and for the rest of the talk, I'm going to assume that this can be performed. So we are going to look only at orders and number field, where whenever you plug them in your algebra system, in your computer algebra system, it actually works. So I'm not claiming that these are trivial tasks. In particular, we already know everything about how to compute the class group and what is cost. But for this talk, I mean, we're going to assume that this can be done. Otherwise, everything else is much harder. So I mean, it's not going to work. All right. An easy lemma from the definition of the picker group and of the ideal class monoid is that the picker group is actually sits inside the ideal class monoid, right? I mean, it's defined as the subset of invertible ideals modulo the same relation. So in particular, we have an inclusion. And note that we have equality between the ideal class monoid and the picker group if and only if the order R is the maximal order of the number field. So the inclusion is clear, the proof that there is nothing to prove. And the proof that we have equality if the order is maximal follows from the fact that over a Dedekind domain, so when your order is actually a Dedekind domain, every ideal is invertible. So everyone can prove that every ideal is locally free or equivalent invertible in the maximal order. Right, so this is what happens when the order is maximal, but clearly if the order is not maximal, we will have like a strict inclusion. And in order to describe the situation in the general case, I need also this concept of multiplicator ring of fractional. So take any fractional ideal I. To that, we can associate a ring. The ring is defined as the colon ideal I over I. One can prove that it's easy to prove that this is a ring. Clearly contains one, it's closed by an addition and also multiplication. But also one can easily prove that this is an order. So in particular, it's going to be a ring that sits between R and the maximal order of the field. Okay, so this is the multiplicator ring. Another way to think about this guy, this I colon I, is as the endomorphism of the module I. So you're looking at R linear endomorphisms of I as a R module, and this I colon I is exactly that. And a third way to think about it is that this is the biggest overorder of R for which I is a module. So if you pick something bigger, I is not going to be closed under multiplication by this element. Okay, so it's the biggest one. So in some sense, it's canonical with respect to the ideal I. Okay, and lemma, quite easy to prove, I'm going to prove it for you, is that the ideal class monoid of an order R contains not just the picker group of R, but the disjoint union of the picker groups of every overorder containing R and contained in the maximal order of K. So the proof goes as follows. So you pick any fractional ideal and let S be any order between R and the multiplicator ring of I. So in particular, I is closed under multiplication by elements of this S, because S is inside the multiplicator ring. And if I is invertible in S, that is, I times S colon I is equal to S, then one can easily prove by the equalities that I wrote here that S is actually equal to the multiplicator ring. So if the ideal I is invertible in some overorders, then this overorder must be the multiplicator ring. So that's really like the ring that you need to look at when you consider the fractional ideal I. So when I is any fractional ideal, you should actually think of it as a fractional I colon I ideal. So this gives you, this is the right ring for which you want to look at it as a module if you want to study the arithmetic properties of the fractional ideal I. Great, and this in particular proves that the union above is disjoint. So an ideal can only be invertible for one order. Note that in this slide and in the whole talk, I'm not allowing extension of ideal. So for example, if you take an ideal with multiplicator ring R, and R is strictly contained in a maximal order, then I times OK, I times the maximal order is going to be a different set of elements with respect to I. It's not the same, it's strictly bigger. So it's a completely different ideal. So we don't allow that. Okay. All right. So this is the easy case. So this lemma tells us that whenever we have an equality here, so whenever the ideal class monoid of R is equal to the disjoint union of the picker group, we are done, right? And that's the usual case. So most of the time, so usually here is a very technical term. It means that whenever you go to the supermarket to go to the shelf of orders, you pick a random order. Well, that for that order, there is a very good chance that the ideal class monoid is just going to be the disjoint union of the picker groups. But if this is the case, which is luckily the general case, then we are done, because we just need to compute the overorders of R and the picker groups of R. So I already told you how to compute efficiently the picker group of every order. And to compute the overorder of R, one can, for example, follow one can look at the paper by Tommy Hoffman and Carlos Circana. This is a recent paper. I'm not gonna give a detailed explanation about how this is done, but the trick is to first compute all the overorders by searching for minimal overorders. And one can prove that every minimal overorder of R is going to be contained in the multiplicator ring of a singular prime ideal. This reduces the question to a linear algebra problem over a finite field, so vector spaces over a finite field, and this can be done very efficiently. So their algorithm is very efficient, it's very good. So we can compute all the overorders of R, we can compute the picker group, and if we are in the usual case, then we are done. The ideal class monoid is understood. We have this disjoint union of the picker. So more precisely, this equality happens if and only if the order R is a bus order. Bus means that every overorder S is a Gorenstein order. And Gorenstein order were studied in the paper by Oyman-Bas with title On the Ubiquity of Gorenstein Order, and I hope that you accept the word ubiquity as a proof that this is actually the usual case. So these happen very often. Most order are bus, so most of the time we have this equality, but not always. And we really want an algorithm that works always. So also when we have these inclusions, that the disjoint union of the fix is not equal to the ideal class monoid. And we already have seen an example, right? The previous example that I gave you, the example that I gave you before, is simple number field with polynomial defined by a polynomial of degree 3. It's already a case where the monogenic order Z alpha is not a bus order. Indeed, we have 4 isomorphism classes. So the first 3 were orders, were isomorphism classes of orders. And one can compute that the picker group of the monogenic order is trivial. It consists only of the principal ideals. By the surjectivity of the extension map, we get that also the class group and the picker group of S are trivial. So there are no other invertible ideals with that as multiplicatory. But we have this mysterious 4th isomorphism class, this ST. And here again are the Z bases where alpha is again equal to, where F is again equal to alpha. Sorry, typo repeated. And I'm claiming that this ideal ST is a non-invertible ideal with multiplicator ring equal to S. And this is another way to say that S is not a Gorenstein ring, or equivalently, or in particular, that Z alpha is not a bus order. So here we have like the disjoint union of the picker groups, this free guy, plus this extra 4th class that we'll need to understand how to compute. All right, so we want an algorithm that handles also these unusual cases, that always works, whatever happens. So the way to solve this problem, as usual when you do number theory, is to first look at it locally. So we want to study local isomorphism classes first. This was started by Dade, started and probably also finished by Dade, Talsky, and Zassenaus in this paper that was published in 1962. Amazing paper, very nice to read. They introduced the notion of weak equivalence between two fractional ideals I and J. And I'm going to give you like 3 equivalent ways to formulate it. So the first one, as I said, is of local nature. So we say that 2 fractional ideals are weak equivalent if their localizations are isomorphic at every different prime. Second, this is equivalent to say that 1, so the unit of your field, lies inside the product of these double colon ideals. So I over J times J over I. And the third one is that they have the same multiplicator ring, so same endomorphism ring, which I will call it S. and there exists an invertible ideal, an invertible S ideal that sends one into the other. So I'm not going to prove these equivalences. Just maybe if you want to do it as an exercise, the hint is that an invertible ideal in S is a locally principal ideal. So this will allow you to go back and forth from the other statements. But on the, I prefer instead of proving it, I prefer to comment a little bit about it. So yeah, the first definition tells us that this weak equivalence is the local analog of an isomorphism. But observe that I'm not asking that there exists a morphisms, a global morphisms that localizes to an isomorphism. These local isomorphisms can be completely not related one from the other. They can come from different isomorphisms and possibly they cannot be glued together. So this is really a local thing. The second one is my favorite one because it's very easy to implement, and it also tells us that weak equivalence is a very easy thing to test. So we can easily compute column ideals, as I said, in polynomial time. Product as well can be done in polynomial time, and inclusion again is very easy to test when you have like matrices inside a number field. So this tells us that weak equivalence is very computationally friendly. So very easy to check. And the third one is also very interesting because it tells us that, okay, the endomorphism ring of the ideal is an invariant of the weak equivalence. So if they are weakly equivalent, they must have the same multiplicator ring. And second, that we are sort of acting with the picker group. I'm going to be more precise later, but also this last thing tells us that this is it's an abstraction to a local global principle, a local global statement. So we have a local isomorphism notion, but if this ideal L, this invertible ideal is not principal, then the ideal INJ might fail to be isomorphic globally. So it's really a local thing. It's really different from isomorphism. Clearly, if the ideal INJ are isomorphic, then they are weakly equivalent, because if they are isomorphic globally, they are also going to be isomorphic at every localization. But the converse doesn't hold in general. Okay. As the name suggests, again, this is an equivalence relation, and I will denote by this WR, the monoid of the weak equivalence classes. Again, it's a monoid under ideal multiplication, and the proof is again very easy and can be obtained from any of the predefinitions. So we have a monoid of weak equivalence classes. Cool. So we can reconstruct the ideal class monoid of R from the monoid of the weak equivalence classes, but in order to do so, I have to partition these two sets, these two monoids, into sets which are divided by multiplicator rings. So I'm gonna denote by this WSR the weak equivalence classes with multiplicator ring equal to S, and I'm gonna do the same for the isomorphism classes. Since the multiplicator ring is an invariant of both the weak equivalence and the isomorphism relation, this is a disjoint union, and this is actually a real partition of these monoids. Cool. And the main result here is that for any over order S of R, the picker group of S acts freely on the ideal class, on the set of ideal classes with a multiplicator ring equal to S. And the quotient of this action is precisely the weak equivalence classes. Okay, so when you, and computationally, what does it mean? That if you have representatives of the picker group and you have representative of these weak equivalence classes, you just need to multiply all of them to get like distinct representatives of the isomorphism class. And this is because the action is free. So they cannot like hold together. So that's computationally is very interesting. We know how to compute the pick of S. If we can compute this WS of R, we get the ideal class monoid with multiplicator ring S. And then you just repeat for every other order and you glue them together and you get the whole ideal class monoid. Okay. Cool. So now the question is, how do we compute this WS of R? So these weak equivalence classes with multiplicator ring equal to S. And here role will be played by the ideal ST, which is the trace dual of an order S. So the trace dual is the set of elements of the number field such that the trace of X times S is an integer. This is a subset of the integers. Okay, so it's a dual with respect to the trace map. And again, this is defined basically only by linear algebra, so it's very easy to compute as well. So this is also a cool thing. And yes, this is T. I mean, I chose the notation because the ST in the example was precisely the trace dual of that order. Okay, so now you really know what it is. So let T be any overorder of S such that the extension of ST is invertible in T. So we are really modifying now this idea. We want something strictly bigger of S, and we want the ST times this overorder T to be invertible in the order T. So there always exists such an overorder. You can take T to be the maximal order, right? So when you extend any ideal to the maximal order, this is going to be invertible. But for computational efficiency, we want this order to be the smallest possible that satisfies this property. Now let I be any ideal with multiplicator ring S. So anyone that will fall into this set of weak equivalence classes that we are interested in. And there is this magic relation that I times this trace dual is actually equal to the trace dual of the order that I defined above. And it follows then that if IT is also invertible in the overorder T, because if I multiply by IT is invertible, then also I is invertible, right? And this tells you that up to weak equivalence, we can assume that the extension of this ideal I is actually equal to the principal ideal generated by 1. So the way to do this is it goes as follows. So we have a surjective map from the picker group of S to the picker group of T. Since this map is surjective, we are allowed to modify our ideal by invertible ideals. If you remember weak equivalence, one of the equivalent definition of weak equivalence is that you can multiply by an invertible ideal and you're not changing the weak equivalence class of the ideal. We can multiply by an appropriate inverse and assume that this ideal extended becomes the ideal generated by 1. Okay. This equality here, I times T equal to T, immediately implies that the ideal I, this particular representative, is inside T and also contains the relative conductor of the order S inside T. So by this equality, we can immediately deduce by very simple argument that we have this relation, we have these inclusions. So we are modifying our ideal with multiplicator ring S into an equivalent one, a weakly equivalent one that sits inside these two specific ideals. And this proves that we can find all representatives of the weak equivalence classes of ideals with multiplicator ring equal to S in the set of fractional ideals that live between this relative conductor and this overorder T that satisfies this invertibility property. Okay, and this set is in bijection with the sub-S modules of the quotient T over F. And this quotient, since it's a quotient of lattices, is a finite quotient. It's a finite set. And very often it's not too big. So we can just enumerate all the sub-S modules, and then we mod out by weak equivalence. And by the second of the definitions of weak equivalence, we know that this is a very easy operation, so we can efficiently do it, and we get all representatives of the weak equivalence classes. Great. So we know how to compute this WSR. A quick recap of what I said in the last slide, in the last couple of slides. So now we know how to compute the WSR. We take the action of the picker group, it's pretty nice action. We get all isomorphism classes with multiplicator ring S. We repeat this procedure for every overorder S, and we can compute all the overorders by the Hoffman-Cercana paper. And we get the whole ideal class monoid. Hurrah. We are happy. We can compute ideal class monoids. We have an algorithm. And this algorithm, as you remember from before, tells us a way to compute representatives of the conjugacy classes of matrices when R is chosen to be the monogenic order defined by our characteristic polynomial. Great, first problem solved. Also, observe that by what I said, WS of R is a finite set, necessarily. The picker group is also a finite set. And this tells us that the ideal class monoid of R is also a finite set. And this was maybe not obvious at all from the initial definition. We were just taking all fractional ideals and modding out by isomorphism. And this is a proof that the picker group, that the ideal class monoid is a finite set. Cool, we have it. Right, so as I said, we have ICM, we have the conjugacy classes of the matrix. Great. Now the second problem, the isomorphism testing. So in the slides that I presented before, there are actually all the ingredients to give an algorithm to test isomorphisms between fractional ideals, or if you prefer, the conjugacy test between integral matrices. This goes as follows. So you take two fractional ideals, I and j, and let's call S the multiplicator ring of one of the two. Then these two ideals are isomorphic if and only if they are weakly equivalent, and the colon ideal sending one into the other is a principal S ideal. Okay, the proof goes as follows. So we know that isomorphism implies weak equivalence, because weak equivalence is just a localization of your isomorphism. So if the two ideals are isomorphic, they're definitely weak equivalent. And also it's easy to prove that, so we know that if they're weak equivalent, that they differ by an invertible ideal L. So I is going to be equal to L times J. And then it's clear that if these two ideals are isomorphic, this ideal must be principal. It's pretty easy to just see by localizing the original thing and saying that L must be a principal ideal. And conversely, it goes the same way. So L, one can prove that this L must be I colon J, basically by definition of the colon ideal. And then we have that this is principal if and only, if the ideals are isomorphic. And the generator of this ideal is going to be the element that induces the isomorphism. Right, but this is also very nice from a computational point of view. So I told you that checking weak equivalence is very easy. And second, if we know the picker group of S, as I said before, we also know that it's how to solve the discrete logarithm problem inside S. And in particular, we know how to solve the principal ideal testing. So we can tell efficiently if an ideal is principal, if a fractional S ideal is principal. Right, great. This gives us an algorithm to check if two ideals are isomorphic without requiring I and J to be invertible in the beginning. Great, so we have solved also this problem. Let's give an example. So now we take a different polynomial of degree 3. Coefficients are 31, 43, and 77. Right, so this diagram represents the lattice of all the overorders. So here you see Z alpha. I'm looking at the monogenic order. And the last one at the other extreme, we have the maximal order of the number field defined by this polynomial H, right? And all the one in the middle, S2, S3, and so on, are all the other overorders. The integer next to the order represents the size of WS, of WSI of Z alpha. So the weak equivalence classes with this order as multiplicator ring. So for example, the monogenic order is a Gorenstein ring. So every ideal is going to be weak equivalent to itself. The same holds true for the maximal order. But in the middle, we have some orders where there are two non-weak equivalent ideal with that order as multiplicator ring. So for example, S2 has two weak equivalence classes. In particular, if you from what I said before, I think you can probably deduce what is the second fractional ideal, and this is precisely the trace dual of the order. So if this order is not Gorenstein, then the trace dual is going to be a non-invertible ideal with that ring as multiplicator ring. So yeah, and the label of the edges, so the edges are inclusions, obviously, and the label is the index of the inclusion. So this monogenic order is index some power of 2 inside the maximal order. All right. And here I represented only the weak equivalence classes because from what I said before, you just need to act with the picker group to get the isomorphism classes. So these weak equivalence classes are an interesting thing to look at when you want to consider non-invertible ideals. All right. Example 2. So everything that I told you so far generalizes basically word by word to the case when the polynomial H is not irreducible, but a product of distinct irreducible polynomials. So it's square free. The only difference, I think, is that when I said non-zero, it should be replaced by non-zero divisor. So really, everything that I told you so far works in exactly the same way. The problem is that when you consider a monogenic order in a product of number fields, this tends to be not isomorphic. Actually, I think it's almost never isomorphic to the product of the monogenic order. So it tends to be much farther down for the maximal order. And the situation tends to be a lot more complicated from a computational point of view, even if theoretically it's exactly the same. The procedure, the proofs goes exactly the same. And this picture, I think, it represents the situation tends easily to be a lot more complicated. So this one here in this corner is the monogenic order of the polynomial given by this quadratic polynomial times this cubic polynomial, so here. And the other corner is the maximal order of this étale algebra. So it's the maximal order of this quadratic field times the maximal order of this cubic field. And there is a lot of stuff happening in the middle. And I'm using the same notation as before. So edges are inclusion, the label on the edge is the index of the inclusion. So we have singularities at 2, 3, and 37. And the number inside the vertex represents the number of weak equivalence classes of ideal with that ring as multiplicator ring. And there are a bunch of 1s, some 2s, but also some 6s here in the middle. So stuff can get pretty wild pretty soon. So we get like a lot more ideals that are not invertible, and they are not even weak equivalent to each other. Great. So example 3, what happens to the matrices? Let's say a few words about what happens when we look at actually isomorphism of ideal. Can we say what is the matrix that sends one matrix into the other? What is the matrix realizing the conjugation? So we consider the same example that we had already a few times, so x3 plus 10x squared minus 8. I take these two ideals, I represent them by z basis, since this is convenient for what we are doing. And we can verify that I and j are isomorphic, and actually they're both isomorphic to the monogenic order of the alpha. More precisely, we have that alpha squared plus alpha sends the ideal j inside the ideal I. I apply the algorithm, and I get the matrices that corresponds to the ideal class of I, to the ideal class of j. And then I define this matrix V, and V represents the z basis of the ideal j multiplied by this alpha squared plus alpha, written with respect to the z basis of I. And again, if you look at the proof of the Latimer-McDuffie theorem, this tells you that V is the matrix realizing the conjugation between the matrix Mj and the matrix Mi. So we have this thing. So from the isomorphism, so the solution of the isomorphism problem, you actually also get explicitly what is a matrix that realizes the conjugation. Clearly, this matrix is not unique, as in the same way as the element realizing the isomorphism is not unique. You can multiply it by any unit of the multiplicator ring, and it's still going to be a perfectly fine element realizing the isomorphism. But still, it's very explicit. We can get it explicit. All right. This is everything about example 3. And now in this last slide, I'm going to tell you about a bunch of generalizations of the algorithm and proofs and theorems that I told you about in this hour. So the bijection between conjugacy classes of integral matrices and isomorphism classes of modules lying inside a product of number field holds in much greater generality than the cases that we have seen. So we restricted ourselves to irreducible polynomial, irreducible characteristic polynomial. But you can actually take any characteristic polynomial, any minimal polynomial, and there's going to be a similar bijection between conjugacy classes of matrices and some modules lying inside some number fields. And this was studied in Guzzard PhD thesis in 2016. Yes. Also, there is a working algorithm. There's an algorithm that works very well to test conjugacy of integral matrices with no assumptions on the characteristic polynomial. This was done by Tommy Hoffman, Bettina Eck, and Eamon O'Brien in 2019. Right, this algorithm works for any kind of matrix. So it's very general. The algorithm that I've described you outperforms the algorithm in the special case when the characteristic polynomial is irreducible. Also, their algorithm doesn't allow you to construct representatives for the conjugacy classes. So it can only be used for testing conjugacy. So you take two matrices and it's going to tell you yes or no if they are conjugate or not. But if you feed him a characteristic polynomial and a minimal polynomial, it doesn't tell you like representatives.
Okay. I have a question, Stefano.
Yes. Yes.
So this working algorithm, has it a particular complexity? Is the complexity well, or is it like a very big complexity?
So I don't think that the authors like analyze the complexity very carefully. So the way it works, it goes as follows. So it uses basically something very similar to Husserl result and Latimer-McDuffie result to translate the conjugacy problem into a module, an isomorphism testing of modules. Then they take these modules. These are going to live inside some product of number fields. They extend the module to the maximal order of this étal algebra. And there, I mean, you have basically Steinitz theory, so isomorphism testing between modules over a Dedekind domain that tells you if they are isomorphic or not. Then they constructed the automorphisms and see if this isomorphism descends to the original module. So in other words, you need to be able to solve the isomorphism problem for modules over Dedekind domain. So definitely you need to compute the class group and be able to solve the principal ideal problem over Dedekind domains, over ring of integers. So that's definitely a lower bound. Okay. But I think one of the key steps in their proof is also they need to be able to check if some intermediate modules are free over this Dedekind domain, and they need generators, and it seems to be a quite hard problem. So I don't know the details of the complexity, but I think it's exponential, but I mean, because of this kind of step. So maybe sub-exponential, I don't know. It's definitely not like polynomial.
Good, thank you.
You're welcome, no problem. Right. So the algorithm that I presented today, both the conjugacy testing and the representatives, generalize with very small steps to the case when the characteristic polynomial of the matrix is a pure power. So it's a power of a square-free polynomial with integer coefficients. And in addition, we need that the order generated by this M polynomial, which will be the minimal polynomial, is a bus order. So this works by the fact that every module of a bus order is actually a direct sum of fractional ideals. So in this case, you can reduce it to what I said today. So you reduce to testing of isomorphisms of ideals. And yes, so I think the theme of, say, half or a big part of the conference of the school was that the class groups are everywhere, but also ideal class monoids appear more often than what you would think. So we have seen today, in the last days, a couple of talks about abelian varieties and abelian varieties over finite fields in particular. And another application of this ideal class monoid is that there exists an equivalence between the category of ordinary abelian varieties over a finite field of Q with square-free Q-veil polynomial H. So abelian varieties lying in an isogeny class defined by the polynomial H, and the set of fractional ideals of the order generated by F, where F is a root of this veil polynomial. So it's going to be a representation of the Frobenius as an algebraic integer and the Verschiebung Q over F. So this lives inside a number field or étal algebra Qx modulo H. And this is actually an equivalence of categories. It's not just a bijection. So this means that you can count isomorphism classes of abelian varieties in terms of isomorphism classes of this fractional ideal, so the ideal class monoid, but also you get maps, you get isogenies, you get polarizations, you can get all the extra structure that you want in this abelian variety in terms of this fractional ideal. So yeah, this is another application of the ideal class monoid. But this is definitely a topic for a very long talk that might be another. And this is everything I wanted to tell you. So thank you for your attention.